Okay, probability. So last we wrapped up on the binomial stuff. Next up is continuous probability. And continuous probability is going to be a lot similar to the stuff you've learned in integration, oddly enough. That is because the way we calculate probabilities of continuous random variables is to first plot the area function and determine that the area under the graph is the probability of any given event occurring. So as for what continuous random variables are, these are the things that have no discrete specific values that can be assigned to them. Normally these are the things that we can measure, right? Like measuring the length of an object, you could say it's a 1 meter object, and that would be accurate to 0 decimal places. But if you measured it with maybe more accurate device or just went to more decimal places, you might get closer to 1.11, or it might be closer to 1.34597, so on and so forth. The number of decimal places is only limited by our ability to measure them. This is what is referred to as a continuous random variable. And so, as I described earlier, the way that we find probabilities for continuous random variables is with what's referred to as the probability density function. So let's say you want to find the probability that your outcome is between some lower bound A and some upper bound B. What you are trying to do in this case is find the definite integral from that domain of the function itself. And as for some other rules that matter for this, because the area under the curve is given as, or is interpreted as probability, it follows that if you were to integrate over the entire domain, entire valid domain of the function, you should get a value of 1, because that would mean that you have summed up all outcomes in the scenario that you're given, and that should equal a final probability of 1. Here's a pretty standard probability density function. They like to use circular functions for this sort of thing, though other functions are totally valid as well. And one of the most standard questions is to just say, hey, prove that this is a probability density function. There's going to be a couple of main criteria for this. The one that matters most is going to be that the area under the curve is equal to 1. And so if you know the function is defined from 0 to 6, then you want to make sure that doing the definite integral from 0 to 6 gives you a value of 1. So if we were to do this tech-free, first of course we have to anti-diff the function on the inside, getting us our capital F of x, and then finally doing the capital F of top minus capital F of bottom. Sorry, what have we done this lesson? We're introducing a new topic, continuous probability. This whole idea that area under a curve can be represented as probability. And yeah, so if we do our capital F of 6 minus capital F0, simplify the circular function stuff down, you will find that it ends up equaling 1, thus proving that you have a probability density function. Technically speaking, there is another criteria, and that is that the function needs to be greater than or equal to 0 for the entire domain, or in other words, can never go negative. And the reason why it can never go negative is because that would imply negative area, and therefore negative probability, which we can never have. This is less important because it just doesn't come up pretty much well, I don't think I've seen a function that you get that doesn't stay entirely above the x-axis, but it's worth just remembering that negative area would be negative probability and therefore not valid for a probability density function. A nice follow-up question to that is less about proving that what you have is a PDF, a probability density function, but rather solving a coefficient to force it to be a probability density function. In this case, they're literally showing you, they're literally telling you that k should be equal to 2, and it's a show that question. But you solve it the same way regardless of if they say show that. which is to, again, make the whole integral equal to 1. A function can only be a probability density function if the total area under the curve is equal to 1. So we do exactly that. Domain is from 1 to 2. Integral boundaries are going to be from 1 to 2. Antidiff to get your capital F of x, and then do your capital F of top, take capital F bottom. Simplify, 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 you will arrive at k equals 2. Thus, if we had k equals 2 here, the area under the curve would be 1. No other k value would work to make this a valid probability density function. Cool so far? Any questions? Okay. Another nuance on this is forcing a particular domain to make the function a probability density function. So in this case, the function is fully defined, there's nothing we can do about that, but the domain has the k's in it instead. Once again, anytime you're trying to force a probability density function, the whole point is to make the integral of the full domain equal to 1. So the domain being k to k plus 1, that makes our integral bounds k to k plus 1. Force that whole thing equal to 1. And in the case of circular functions, they're very likely to put a limit on what k has as a domain, because you would get infinite solutions otherwise. So make sure you put that in your CASSOL as well. And yeah, this will pretty much always be a CAS question. It's unlikely that the domain they give you is nice enough to solve particularly well. By hand, that is. Okay. Here's one of the other standard questions, which is to simply just find the probability over a certain domain. Find the probability from x equals 2 to x equals 4 for this particular function. Whenever you're trying to find probabilities in a continuous probability scenario, with a probability density function, it's the only time functions show up in the probability area of study. Anytime this is the case, those boundaries become your integral boundaries, and that's it. So what you'll find is pretty much this entire little subset of probability is just finding area under curve, definite integral, definite integral, definite integral, and just different ways of doing that. Previously we were setting them equal to 1 because we were forcing it to be a probability density function. In this case, we're already given that it's a probability density function, and we have to find some certain probability for it. Probability is from 2 to 4, integral bounds 2 to 4. Antidiff, capital F of 4 minus capital F2. We all cool with that? Any questions there? Cool. Next up is what's referred to as a percentiles question. It's kind of technically something that should show up in the statistics section here, but they're all quite intermingled in this way. I don't think I understood what a probability density function is. Yeah, that's fine. So the probability density function is essentially a curve that is supposed to map the likelihood of certain events. Now it's a bit nonsensical with the ones that we use because these wouldn't be used in like the real world, right? But what you'll find is that there is such a function that we do use, genuinely speaking, actually in the real world. It's a much more nuanced function beyond just a simple cosine. But to give you like an example, we'll take a sneak peek at the normal distribution. So this is the bell curve. You guys might have seen this before. Your grades are distributed in some sort of bell curve like this. And that has an equation. It has this equation specifically. And the idea behind what you're looking at here, is that each area slither under this curve has a certain likelihood of occurring, or at least has a certain area underneath it, and depending on where you are on this curve will be basically what your grades are and what the likelihood of you achieving that grade is. So let's say you've gone all the way from grade 0 to grade 100%, right? The likelihood of you getting 0 is probably pretty damn low. The likelihood of you getting 100% is also pretty damn low. So your grades are likely to be centered at some sort of mean, and that'll be, you know, some percentage, whatever this little slice of area is, will be the likelihood of you getting that particular grade. So on and so forth. The larger you make these slices up, depending on where you put them, the area under the curve is the likelihood of you being in that boundary. The x-axis stuff are the outcomes themselves, and the area under the curve over a particular domain is the likelihood of your outcome being within some lower bound and some upper bound. Is that a bit clearer as to what's going on with probability density functions? Cool. Good to hear. So next up is a new take on that, which is you actually know the probability ahead of time. Find probability x greater than a is equal to this, right? So the probability is already known. This is the probability. What isn't known is the lower bound of the interval. It's find the value of a such that if I were to place a lower bound, I would get an area of 2 minus root 214. So a good way to do this would be maybe with a number line. So if it's x greater than a, it means you have a on one point of your number line and just shooting all the way right on the other side, which will max you out at 15 pi. That's why we're able to identify what the upper bound should be, 15 pi. It's x greater than some value, so we're pointing to the right all the way up to the max that we possibly can. We don't know what that lower bound is other than the fact that it's a, so we leave it as a. Then from there, because we know that the function, when you integrate over that domain, should equal 2 minus root 214, we make the definite integral equal to 2 minus root 214. And then we just solve from there. So again, this is an integral, it equals something. So to evaluate this left-hand side, we're going to first antidiff, and then do capital F of 15 pi minus capital F of a. Still maintaining that right-hand side equals. Sub in your values, simplify, 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 and eventually, at least in this case, you'll get it down to a circular function equation, where does sine equal root 2 on 2? That's going to be pi on 4 and 3 pi on 4, and any given number of 2 pi n iterations after that. Simplify everything down, making sure we get the a back on its own, and then essentially choose the value of n, the iteration that you go forward or backwards in, such that it'll actually fit within our domain. Because remember, a is a lower bound of a domain. It's got to fit within here somehow. So if I chose n was 0, for instance, I could have access to 3 pi on 2 or 9 pi on 4, none of which is even close to 9 pi. So next best bet is to try n equals 1 and see which of these gets me within my domain. Only this one gets me within my domain. That one had a bit more going on for it. This is something you could also CAS solve. This would be a matter of wrapping this whole thing in a CAS solve for a, and then putting a domain on a as 9 pi to 15 pi. So if you had this in a tech active, that's how you would do that. If you had a tech free, well, we've just discussed that now. Any questions about any of that? Last up is conditional probability. So we looked at this last time, I believe, as well. Conditional probability always has a dedicated formula. First thing we've got to do, identify what it's actually asking us. So find the probability that the task takes between 2 to 3 hours, given that the task took less than 4 hours. Keyword given that, implying conditional probability here. Find this given that something else has already occurred, or some other known information about the scenario already exists. That is implying conditional probability. The way you set it up, the thing that they say find is going to go on the left hand side. Find the probability, task takes between 2 to 3 hours. So that would be X being between 2 and 3. Given that the task took less than 4 hours, since that's the thing that follows the conditional, or that is the conditional, that goes on the right hand side. X less than 4 hours. As for then what the equation ends up being, it ends up being the intersection of both of these things. So this interval intersecting this interval, that's your intersection symbol there. And then whatever your conditional is becomes the denominator of the equation. So let's intersect the two things, and then conditional becomes the denominator. This is how you start all conditional probability questions. Identify what the thing you're trying to find is, and what the conditional is on it. Once you're done with examples, could do a bit of recap plus explanation. Joined a bit late, feeling unsure about continuous probability. Yeah, we can. Yeah, we'll finish this example and we'll do some practice questions, and I'll pretty much just walk through the concepts as we do it as well. But okay, so intersection of these two things. Best way to do it, number line. So x being between 2 and 3, that would look like this. Now, what you might notice as different from discrete is that when you're dealing with continuous, these inequalities of non-inclusive, I did use inclusive here, but to highlight a key difference, non-inclusive and inclusive in the context of continuous is irrelevant. You treat it the exact same way. So from 2 to 3, whether I used non-inclusive or inclusive, you still have a domain of 2 to 3. And the reason why is because in discrete, we would have to round inwards because the next available outcome is an integer, right? Like a dice roll. You can't have a 1.5. You have to roll a 1 or a 2. But with continuous, the whole discussion at the beginning was that it's about measurements that have arbitrary accuracy. They can go to any number of decimal places. So the next number after 2 isn't 3, it's 2.000001, so on and so forth, with any number of decimal places. And so because there is such a small step between values on inside versus outside, you treat any given set of inequalities as basically the same way you would treat inclusives. Anyway, so that's why that's the way that is. From 2 to 3, you're still including 2 and 3, basically. X less than 4, same thing, inclusive of the 4 all the way down to the absolute lowest it can be, which is the absolute lowest on the domain, 0. To find the intersection of those two things, you just look at where they overlap. And that's just going to be this blue line bit here. Right? Where do these two things overlap? Just in the middle here. So this whole thing, you basically just knock off that right hand side. It's just 2 to 3. that now gives you two separate things to solve for. We've already looked at how to solve both. How do you solve probabilities between 2 and 3? Well, you set up a definite integral between 2 and 3. Find a capital F of x, capital F of 3 minus capital F0, and you have your numerator. Really good idea to separate these out. Don't try to do these all in one line. Next up, this one's a little bit less obvious because I don't exactly explicitly tell you what lower and what upper is. X less than 4 just means that 4 is your upper, and whatever the lowest number on your domain is becomes your lower bound, which in this case is 0. So all x less than 4 means you're doing from 0 to 4. Your capital F of x will be identical, and these may or may not be. So capital F of 4 minus capital F0, again just simplify all the way down, and you have your denominator. Numerator divided by denominator, this thing divided by this thing. Do a bit of fraction math, and you'll have your final answer for your probability. Big mess of math. But that is about as far as the fundamentals of continuous probability go. It's all about the outcomes that you are looking at in the scenarios are on the x-axis. They are x values. And in order to find certain probabilities, what you're doing is finding the area under the curve over that domain. That's the gist of it. Let's give it a practice. First up, show that the function is a probability density function. So again, the key thing here was that for a function to be a valid probability density function, it means the area under the full curve over the full domain needs to be equal to 1, because that represents you finding the probability of all possible scenarios, and all possible scenarios need to add up to 1. I guess outcomes, sorry. All possible outcomes in a scenario need to add up to 1. So that means we are finding the area under this curve from a 3 to 6, and we're hoping that the answer will come out to be 1. F of x is 24 on x cubed. Capital F of x, we add 1, so it's 24 on negative 2 x squared. That's going to be negative 12 on x squared as our antidiff. Then from there, our domain was from 3 to 6 as per the piecewise, so we'll do capital F of 6 minus capital F of 3. Minus 12 on 6 squared minus 12 on 3 squared. Okay, minus 12 on 36 plus 12 on 9. Why does that feel really off? Okay, 12 on 36 minus 1 on 3 plus 4 3s are 12. Okay, no, it's fine. 3 on 3, which is 1. Wow, that was really on tilt. So because we get a final answer of 1 there, we have proven a probability density function. Total area under the curve equals 1, because total probability of all outcomes in a given scenario need to add up to 1. Any questions? Question 2. Again, we have a probability density function, but it's got a k in it. And it's saying determine the constant k such that f is a valid probability density function. Again, the whole point of the probability density function is to make sure that it equals 1 over its full domain. So I want to make sure that the integral, in this case, from 0 to 2 is equal to 1. 0 to 2, f of x is equal to 1. Should be a dx in there. So we're going to anti-diff. Once again, capital F of x squared is going to go to a third x cubed, kx is going to go to k on 2 x squared, and plus 1 is going to go to plus x. From there, our domain, our integral bounds are from 0 to 2, so we are doing capital F2 minus capital F0. That's going to give us a third 2 cubed plus k on 2 squared plus 2 minus capital F of 0. That's going to go to 0, that's going to go to 0, that's going to go to 0. And the whole thing needs to equal 1, right? The whole domain, the whole integral of that boundary needs to add up to 1. How do I keep tilting my work? Anyway, 2, 4, 8, and then divide by 3, 8 on 3, 2, one of those cancels out, leaving you with just 2k plus 2 equals 1. 2k is equal to 1 minus 2, so minus 1, and minus 8 on 3. 2k equals, so minus 3 minus 8 on 3. K equals 8, 9, 10, 11, minus 11 on 6. So if we were to choose k equals minus 11 on 6, we would get a valid probability density function, because the thing is we have forced the area under the curve, area under the full curve, to be equal to 1. Any thoughts or questions about how to handle those kinds of questions? All about proving or forcing a probability density function. Okay. Next up, they asked to sketch the graph. Sure, why not? Function is equal to 12x squared times bracket 1 minus x. And we're doing it from 0 to 1. You'll find these are often quite small things, because they have to have an area of 1 in them, so they are unlikely to shoot quite high or run quite long. Maybe a little bit bigger than that. And what you'll find is there are often these nice little curves that fully touch on either side, making and entirely ensuring that they stay above the x-axis for the whole duration. Anyway, that's the graph. finding the probability of x being less than 0.5, the values that they're mentioning, since it's x, x less than 0.5, we're talking x-axis. So if we think about the valid domain here of 0 to 1, x being less than 0.5 means we're talking from 0 to 0.5. So in other words, if I were to draw out what that might look like, we're trying to find the area that would be contained from left to right up until this point here. Not going to be 50-50, even though domain is from 0 to 1, because of the way that our function is lopsided. We can see as a rough estimate that the area is going to be less than 50%, therefore the probability is going to be less than 50%. So how do we find the area under the curve for it? Definite integrals. Function 5 out of 16, 31%. Part C we already talked about, shading the region which the probability represents. I wonder actually if I can get the CAS to put it in their bounded area. This graph, this graph. No, it doesn't look like I can select it. Ah well, it's this stuff in here. Question 4 is basically a rehash. Find the constant k. Again, probability density function. So if you've got coefficients in there that you otherwise wouldn't know how to solve, a good place to start is forcing the area under the curve to be equal to 1 over the valid domain. This one will solve with the CAS. So domain is from 0 to infinity. It's all y greater than or equal to 0. It says the letter y. We don't have to necessarily think about it as y-axis values. Much easier, of course, to just treat it as if it says x. As a refresher, infinity is in the pi symbol section. And yeah, the rest is just plug and play, just making sure you put an actual multiplication symbol between the k and the e. Otherwise things might get a bit weird. Forcing it equal to 1. That's actually kind of interesting. I didn't even put a CAS solve on there and it kind of just did it. Nice. I was kind of putting it there as a placeholder, but then it just sort of solved it. Oh well, that's cute. Now that we know that k is 1, find the probability of y being less than or equal to 2 becomes easier, because now we have the actual function that we're working with. If we didn't have our k value, we would just be having to set our upper bound to 2, lower bound to 0, and then whatever comes out will be in terms of k. But because we obviously know that k is equal to 1, we're going to go ahead and replace that. And just for peace of mind, I'll do it at the beginning as well, and you'll see that you get the same answer. Okay, question 5, start stepping things up. Okay, quarantine period of a certain disease is between 5 and 11 days after contact. The probability of showing the first symptoms at various times is described by this probability density function. So the thing on the x-axis is the quarantine period itself, and the probability of showing symptoms during the quarantine period is given by the area under this function. It's quadratic, we can see that off rip. Sketch the graph of the function, sure. Function is equal to 1 on 36 times x take 5 11 take x. Okay, what's this going to be? So it's going to have intercepts at 5 and 11. So let's go ahead and zoom that out to maybe 20. Is h of x still here? No, just flat out disappeared, huh? Nice. Now, there's one thing wrong about what's just been drawn here. Can anyone suggest something that's a bit weird and how we can correct it? Think about what it takes for a probability density function to be valid. Think about the significance of the statement. The quarantine period for a certain disease is between 5 and 11 days after contact.
Would it be greater than X?
Say again, sorry?
Would it be greater than X because doesn't everything have to be positive?
Everything has to be positive, yes, so it has to be fully above the x-axis. That's right. And so, yeah, the statement there that it's between 5 and 11 days means it's valid only for the 5 and 11 days. So, if we were to restrict the domain as such, we would see that it's above. 5 less than equal to x less than equal to 11. Fully above, and again it's quite tiny. They usually do. Awesome, we have our graph over its fully valid domain. So what you'll notice is in question 5 it didn't explicitly tell you t is between 5 and 11. You had to be able to read that from the question itself. So like answering part A properly means not just sketching a quadratic, it means sketching a quadratic over the valid domain. But okay. Part B, find the probability that symptoms appear within 7 days. Within 7 days. Again, this valid domain that we have is going to be important here. So if symptoms have to appear within 7 days, what effective domain are we talking about here?
Five to seven.
5 to 7 is correct, yeah. Not 0 to 7, but 5 to 7, because we've had that lower bound of 5. Nice. So when it comes to solving our probability, 5 to 7. That gets us our probability. Excuse me. Part C. Harder again. It's still find the probability that symptoms appear within 7 days, but it's given that we know they've already appeared after 5.5 days. The key wording here implies a conditional probability. Does anyone remember the generic way we do conditional probabilities? We would start with our basic probability statement. Find the probability that symptoms appear within 7 days. We already know what that one means. That one means probability 5 less than equal to x less than equal to 7. Again, the use of inequalities is irrelevant for which ones you want to use. It ends up being the same thing. Then we use this pipe symbol. Same thing you use your domain as. Given that they appear after 5.5 days, so symptoms appearing after 5.5, that is our generic probability statement for conditional probability. Find this given that this has occurred. How this is resolved. We find the intersection of the two things and then divide by whatever the conditional is. So intersection of this and that, dividing by the conditional itself. The intersection of these two things can be best explored on number line. So the numbers of relevance here are 5, 5.5, and 7. 5 to 7 looks like this. Greater than 5.5. What's our maximum? Our max is 11. So the other number of relevance would be 11. Greater than 5.5 means going from there all the way up to 11. Intersection of two things is just where they overlap. So that means here and here, meaning the intersection of these two things is going to come out to be 5.5 to 7. Probability of finding that. The conditional, there's nothing else to simplify there, it just is the conditional probability of x being greater than 5.5. Probability x greater than 5.5. We now have the two things that we are trying to find. We want the numerator, we want the denominator. Both of these are probabilities over a given domain, hence we're doing a definite integral over that domain. So for the first one, it was 5.5 to 7. That gets us our numerator. Last one was just greater than 5.5, which maxes out at 11 as per the question. This was our numerator, dividing by our denominator, and we'll see that we get a certain probability, roughly 24%. This is how this ends up working every time. You start out by identifying what the probability statement is and what the conditional is. From there, you start creating your conditional probability formula, which is again, arranging things in the right order. You now need to know that you're finding the intersection of the two things and dividing by whatever the conditional probability is. Intersection, best resolve with a number line and just looking at where the two intervals overlap. That allows you to simplify what you got on top, than just having two separate things with an intersection symbol between them. Then resolve them individually and then divide through, because, well, that's what this says. It says divide this by that. Any questions? We can repeat the exact same thing for part D. Again, it's find probability of symptoms within 7 days. This time the conditional is given that they appear within 10 days. So, only slightly updating what's going on. So, within 7 days, we had 5, we had 7, we had, now 10 is the next thing of import. Probability of symptoms within 7 days was this. Probability of symptoms within 10 days would be this. Intersection of the two, it's as if the conditional didn't matter. It will matter because we're still dividing by it at the end, but it doesn't necessarily change what your numerator is going to be. So ends up being probability of 5 to 7 divided by probability of 5 to 10. Because the conditional was within 10 days. Conditional goes on bottom, intersection goes on top. Let's do exactly that. 5 to 7, already done. 5 to 10, coming up. This was our numerator, dividing by our denominator. This one comes out to be a little bit more likely, 28%. That's conditional probability. There's not too much more new questions unless maybe I'll take a scroll through and see if there's anything new here. For the rest of them I'll talk high level until we see something new. Question 6, probability thing. It's got a k in it. It's from 7 to 17. Show that k is pi on 20. Again, whenever it's basically proving a coefficient, we're always forcing the integral of the function to be 1. So that's how you would do part A. Hence find percentage of 2-year-old children whose mass is greater than 16, so that would be 16 to 17 for your integral, or between 12 and 13, in which case your integral is from 12 to 13. Find k means forcing this integral from, in this case, 0 to infinity. It's all t greater than 0. That's pretty common for exponentials, decaying exponentials. You'll shoot them off to infinity. And yeah, exactly. So 0 to infinity, let it equal 1, solve for k. Probability that the bulb will last more than 1,000 hours. More than 1,000 means 1,000 is the lower bound, and you're still setting infinity as the upper bound because that's what the model is expecting. So this will be 1,000 to infinity for your definite integral. These again have some k's in them. They have multiple k's in it though, which is interesting. So let's talk about this one because it's a piecewise function that's split across multiple domains. K is forced positive. First, sketch the graph of the probability density function. Yeah, why not? So these are both linear. To make that a bit more obvious, we can expand the k through and write it in the y equals mx plus c format. So we've got function 1 is kx plus k, and function 2 is negative kx plus k. This one is from negative 1 to 0. This one is from 0 to 1. Since k is a positive number, this will be a positive gradient, this will be a negative gradient. It says that by saying k greater than 0 on question 8. Sketching the graph, y-intercept of both of them is going to be k. X-intercept, let y equal 0, you're looking at plus minus 1. So you're going to have minus 1 and positive 1. From that I was just looking at the factorized versions. The whole k bracket 1 plus x equals 0. K is irrelevant, and 1 plus x equals 0, x equals negative 1. That sort of thing. The exact same is said for the second function. Because I know both the x and the y-intercepts of both, I can now draw what those will look like. bang, and bang. We have this nice little triangle. To prove or to solve for k such that we get a probability density function, it means that we need the area under this triangle to be to be equal to 1. So half base times height. Area is equal to 1 is equal to half times the base of 2 times the height of k. K equals 1. Two and a half cancel, k equals 1. Nice. Now that we have k, the whole thing becomes a lot easier, although not necessarily super easy. Part C, find the probability that x lies between negative 0.5 and 0.5. That's a bit of a nasty question, because no, your CAS can actually do this in one go. If you define your function as a piecewise and integrate from negative 0.5 to 0.5, it will just resolve it. Let's pretend we don't have CAS and we have to do this tech-free. The reason why negative 0.5 to 0.5 is a bit of a nasty domain is because the area is covering two separate curves. We want this little slice in here and this little slice in here, and it's given by two separate things. It's not as nasty as it might seem because of the symmetry nature of what's going on. For instance, area on the left is the same as the area on the right, or vice versa. Area on the right is probably a bit easier to solve because you're using only positive terminals for your integral. Or you could even do, actually no, you wouldn't want to. I was going to say trapezoidal method, but actually no, we do have the equation now. We have k equals 1. We could do trapezoidal method, but not necessary. Integral from 0 to a half. That was a terrible 2. 0 to a half. This is now negative x plus 1. And we're going to double this to get both sides. Just for the record, if this wasn't symmetrical, you would do one slice as its own integral, the other slice as its own integral, and then just add them up together. But because there is symmetry in this, we are making use of that. Capital F of x is therefore, so x will go up to minus half x squared, plus 1 will go up to plus x. So the area that I'm looking for, or I guess more specifically to use the key terminology, I should say probability of minus half less than equal to x less than equal to positive half, is therefore equal to 2 times 2 copies of this definite integral, which is capital F of half minus capital F0. Capital F half, take capital F0. Okay, so we're going to have minus half and then half squared plus half. That's this bit. And then minus capital F0. Put a 0 there, put a 0 there. It'll go to 0. From there, 2 times half squared is a quarter, times another half gets you to an eighth, minus 1 on 8. Plussing a half is the same as plussing 4 on 8. So it's going to get us 3 on 8 times 2 for 3 on 4. Does 3/4 make sense? Yeah, makes a decent amount of sense. That seems to be most of the area. So you can always do a nice little quick check if you do have the picture to go with it, to make sure that your final answer has a decent amount of sense to it. So yeah, I guess key takeaways here, make use of symmetries to simplify the amount of effort that you're putting into it, and make use of the correct terminology. Don't just say like area is equal to this, say probability is equal to all of that, because that's what it's asking. Find the probability x being between negative 0.5 and 0.5. Any questions? Okay, question 9 has nothing really special to talk about. Quadratic, find probability between 0.25 and 0.75. Those just become your integral bounds. Nothing special. Question 10 is effectively a recap of question 8, where you have a split set of functions. You can already kind of tell the symmetrical nature of what's going on already, so a very similar thing of this one's from negative 10 to 0, this one's from 0 to 10, but your probability is split. So you'll just do one of them from 0 to 1, oh sorry, this one will be from negative 1 to 0, this one could be from 0 to 1, and you could add them both together, or just solve one of them and double it, just like we discussed. Solve for k, so in this case it's going to be a matter of doing your definite integral from 1000 to infinity, setting it equal to 0. That gets you your k. Probability that a bulb will last at least 2000 hours, so that means 2000 or more, which means 2000 is your lower bound and infinity is your upper bound. Determine the probability that more than 1.5 thousand litres are bought in 1 week. So x-axis is in terms of thousands of litres, so that means your boundaries are going to be from 1.5 to 2 on your definite integral. Determine probability that demand for petrol in 1 week is less than 1.8, given that it's more than 1.5. Keywording of conditional probability. So less than 1.8 means you're going from 1.8 down to 1 as your first statement of the probability, of the conditional probability. Second one is that it has to be more than 1.5. So that's going to be your conditional. Find the intersection of the two things, simplify it down, divide by whatever this ends up being. If we need to practice conditional probability more, let me know. Happy to spend like maybe even more time in the Friday class as well, doing that sort of thing. But yeah, at this point we have seen every question. But just for the repetitions, we'll keep going. Okay, find probability more than 8 minutes elapses. So that's 8 to infinity for your domain. That's because it's x greater than or equal to 0. It doesn't give you a known upper bound, so it's default infinity. Again, especially for these exponentials, very likely. Find the probability more than 12 minutes elapses, given that more than 8. So you find the intersection of those two things, and then divide by the more than 8. Find probability less than 0.5. That is split across two domains here. So less than 0.5 would be starting in the second domain from 0.5 to 0, and then you then also need to do your integral on the 0.2 as well, because it's got to go all the way down to negative 1. It's less than 0.5 all the way down to it. Because there's no symmetry involved in here, you do have to do these individually. So this one would be a definite integral of this from 0 to 0.5, and a definite integral of this from negative 1 to 0, adding them both up together. Conditional probability, again, just find the intersection of these two things, where they overlap, and then divide by this probability. And lastly, This is just a whole bunch of, again, probability. Probability x less than 0.5, capping out at 0. So 0 to 0.5. Greater than or equal to 1, 1 to infinity. This caps out to infinity. Conditional, I've said that about 50 times. Alrighty, that's time. We've hit all of the key things for, what's this, chapter 15 something or other? 15a. Nice. Thank you for coming. If you have any questions, feel free to stick around.
Thank you.
No worries.
Thanks.
Cheers. Thanks for that.